هنبدأ المحاضرات النهارده. أول محاضرة دكتور Sven. Actually, it's my honor to introduce you, Mr. Sven. Engineer Sven Breuner, who is CEO of VAST Data in Germany. He will talk about the VAST Data future from your HPC Data Platform for hyperscale and zero compromise. Thank you. Please welcome Mr. Sven.
Thank you very much. Just need a second. My name is Sven. Thanks for joining us today and for having me here today. It's actually the first time I'm in Egypt, not only for vacation, and I'm very, very much impressed by how friendly everyone here is and how well educated everyone here is. So it's a big pleasure to be here. With me here today are my two colleagues, Heider, our manager of the region. Maybe you can quickly raise your hand. Heider, hello. And also Eric. Where's Eric? Over there in the back. Hey, Eric, one of the smartest guys that we have in the company, so I'm very proud to have both of them and three of them here today. But let's get started talking about storage for HPC. So what's my background? My name is Sven, as you already know. I'm the field CTO of VAST Data, so my job is to be in the field with you here and learn everything I can about your application so that we can make a better product to help solving your problems. I've actually started my career in HPC back in 2005 at the Fraunhofer Center for High Performance Computing in Germany, where I've worked for over a decade, actually, with many researchers together like you, trying to solve the difficult problems of the society, right? Working especially in applied research, where we're not trying to solve only theoretical things, but things that can really be applied in the industry to move the society forward. That was the main role of Fraunhofer. And at Fraunhofer, I was already involved in storage. I developed one of these parallel file systems that's called BGFS. Still quite popular today, but the times are of course changing, right, from what I did back in 2005. So nowadays we need new approaches. Why do we need new approaches? Well, let's look back to HPC back in the days, how it was when I started back in 2005. Basically a bunch of nerds. I was one of them. Hopefully it didn't look exactly like this, but maybe, I don't know. But basically we were happy if the computers were working at all, right? If anything was able to run across a small set of computers successfully, maybe for a few hours. Our expectations were not very high, we did not solve very tough problems. But in the meantime, since back in 2005, right, when it was still the early days of HPC, so much has changed. It's the IT industry, everything is developing so quickly. Nowadays, HPC is actually keeping the world turning, I would almost say, right? It's so important for, let's say, our financial markets, for our healthcare during COVID, right? I couldn't have imagined it without HPC. It even entertains us in the movies these days and makes these great special effects. It lets us build better planes that took me here to Egypt today from Germany. And it even takes us to other planets. And VAST Data is probably actually involved in all of the use cases that you can see in these slides, and they are all HPC, and they are all still important today and have evolved over the last decade or two. But the world of HPC is changing. Back in the days, it was mostly simulations. So we as the humans try to understand the nature, the atoms, or whatever we try to simulate, and then tell the computer how to calculate what would happen under certain circumstances, right? So the input was typically small, and it took us humans a lot of time to find out how everything works and teach the computer to understand this, and then run simulations that produced some meaningful result. But nowadays this is changing in the thing, in the way that we have AI upcoming. Right? So HPC is basically for me two things. On the one hand, it's the approach how we make applications scale across multiple computers. That hasn't changed. That is still very important because a single computer still is not powerful enough today to solve the big problems of mankind. We still need to scale our jobs across multiple computers. But the applications that we run in HPC, they are changing, right? From us trying to understand everything and then over a long time program the computers to draw the right conclusions. Now we have AI available, and that means the computers themselves can learn. They can now understand things and draw their own conclusions, right? And they can, of course, draw these conclusions much faster than we as humans could do, at least in some areas, right? In general, of course, we humans are much smarter, hopefully still, than the computers, but for certain types of very important problems, the computers can much better understand the situation and draw much better and much faster conclusions. But the computers do not learn the same way that we humans learn. Let's take a child as an example, right? And let's assume we want to teach the child what a cat is. For a normal child, you show it maybe 4 or 5 or let's say 10 or 20 cats, and afterwards the child will understand what a cat is. That's very normal, right? And even if you only showed it white cats, afterwards it will only also recognize that a black cat is also a cat. No problem. For a computer, that's very different. For a computer to understand on an image what a cat is, you need to show it millions and millions of images of cats from all different sizes and angles, in different colors and so on. If you never show the computer a black cat, then afterwards, if it sees a black cat on an image, it will not recognize this as a cat. That's the important thing for the storage that's changing in HPC. So previously, the input in HPC typically was rather small, then we have these complicated algorithms that produce great simulation results, so the output was rather large. Now in AI, it's the other way around. We need a lot of input, right? These millions of cat images in a very abstract example, so that the computer can understand and learn what we want to teach it. It's the same in medical, right? If a computer should detect cancer, then we need to show it many interesting genomes from which it can draw the conclusion when there is cancer automatically. And once it has learned that, then it can of course do this much faster than a human could do and much more reliable. So that's what's changing. The input is now becoming very important, and the random access to the input. Because you cannot show the computer the same images of cats only in the same order, then it will bias towards the last images that you have shown to it. You have to show it these images again and again in different angles and stretching and so on, and in different order especially, so that it's not biased towards the last things that it saw. Again, very different from how humans learn. That's why random access to the data now becomes so important. That's what makes all-flash storage so important these days. Back in the days, we had only spinning disks. They were pretty good at sequential I/O because they have a head inside that needs to seek to a certain position. From there, it can read very fast. But for random access, this access head would need to be repositioned all the time. That would take very long, and that's not working well for AI. For all-flash storage, that's very different. It's only chips. There's no mechanical parts in these drives anymore, so their random access is just as fast as streaming access. And that's why they are so important for AI. So, as a conclusion that I would draw from all this, right, data is the essence of this new era of HPC into which we are moving. That means you always need to have fast random access to all of your data to be successful and at the leading edge for your research. You always need to have seamless access to the data through multiple protocols, because typically it's rather complicated workflows. It's not only a single application that you run, it's a whole suite of applications that you run, and different researchers, of course, run different applications. Ideally, you even want to be able to share your data with other universities in the country, or maybe even across the world, right? So the storage system should also support that through the right protocols. And your data has to be always available, right? If you cannot access your data when you have a good idea and want to do your research, then you cannot do it. That's also a problem. And in the end, of course, it also has to be easy to manage. And that's basically all the things that we try to do at VAST Data to help you. So going again back in time, what did the world look like when we started? Basically, most of the organizations when we started back in 2016 had this rather complicated pyramid of different storage systems. Everyone could already afford a very small, fast, all-flash storage system if they wanted to, but the problem is that the size was so small that you could not really do anything useful with it, right? Given that the large amount of input data is so important for the research. So that simply led to the fact that most of the data was living in what the people call the archive, so a rather slow and based on spinning this large storage system, which did not allow you to do much with the data anymore. So that obviously does not work for AI anymore, right? Let's go to the next one here. That means, on the one hand, the IT infrastructure is very complicated. Users have to move data around between the fast and the slow storage, which will typically prevent them from doing this in the first place because it's so inconvenient. So the research outcome is not great, and that's the actual problem that we're trying to solve, of course, enable these new insights, right? Through fast storage systems that always give you fast access to all of your data so that you can do the great things that you have in mind. So in the vast data world, the ugly, grey old storage tiering model completely goes away because we try to build the single big system that is affordable at larger scale, but completely based on all-flash technology, so that you have always fast access to all of your data, and that of course provides the feature set and the robustness and the ease of use and the different protocols that you need to always have seamless access to your data. And maybe that we must have done something right and exactly at the right time is proven by the fact that VAST Data actually turns out to be the fastest growing storage company in human history, which luckily, of course, brings me among many other countries to Egypt these days. We have originally started the business in the United States, so I'm sorry about this, it's probably way too small for you to see. But we have already partnered with many leading HPC universities and research organizations in the world, which of course makes us very proud that we can work with that. So getting a bit more technical, how did we build VAST Data? Because the main problem with all-flash storage so far has always been that it just became unaffordable at larger scale, right? Otherwise, everyone would be building all-flash storage systems these days already, but typically that's not possible because they just get way too expensive. That's because in storage servers or computers these days, we typically have the third generation of flash drives. They are called TLC or triple level cell flash drives. They are nice and fast, as you would expect from all-flash storage. They have good endurance with back to the number of write cycles that you can do to these drives. But the simple problem is that they are just way too expensive. Luckily, these days we have the fourth generation of flash drives also available. They are called QLC or quad-level cell flash drives. Again, nicely fast, as you would expect. The big advantage of this new technology is that the pricing is much, much closer to the pricing of spinning this. So it helps us to bring the pricing of the hardware very, very significantly down to make them more affordable. But these drives come with a special twist, namely that they can't handle small write operations well, which typically is unavoidable for all kinds of HPC research that there are also small write operations. But the fact that these drives can't handle small write operations well is typically the case why you can't use them at all, even though they are so attractive because of their lower pricing. So, wanting to bring the pricing down, we had to do something special to be able to use these drives, which most other companies cannot use. So, what we had to do was just to avoid small write operations hitting these drives, and we did that by adding a layer of so-called, doesn't matter, I will just go over. We did this by adding a layer of so-called storage class memory drives to the system. They are more expensive flash drives, which does not really matter because they only make about 2% of the capacity of the VAST system. And we use them as a write buffer into the system. So all write operations that come into the VAST system first land on the storage class memory drives, which are almost unbreakable with respect to the number of writes that you can do to them. There we can nicely buffer large amounts of data, and then we asynchronously stage that over to the QLC drives only in large blocks. That's the simple magic of how we avoid hitting small write operations on the QLC drives, and that's how we make them usable for HPC and the systems more affordable. And the third thing that you can see on the left side is that we wanted to be able to run global algorithms across the system. One of these global algorithms these days that you might have heard of is erasure coding. It's a technology to make the systems highly available. That's something we're doing. But another very important algorithm that I will talk more about later is a new type of data compression, lossless data compression, that in the end is important because it also brings the pricing of the systems further down. Right? If you need to buy less hardware to store more data thanks to the compression, then it makes the systems cheaper. System architecture at the top level. Really have to have my mouse pointer over there. I found it. Okay, perfect. Okay, so at the top level, what you see very abstractly here, the monitors are supposed to be the compute nodes, your HPC compute nodes that you have in the system. So that's not the VAST system itself. The VAST system itself consists of these two layers that you can see here, the middle layer and the bottom layer. Let's start at the bottom. There we have the Nvme Enclosure. It looks a bit fat here in the picture because there's so much text, but it's actually just a 2 rack units enclosure that you can see here in the corner. It contains a fixed number of 44 of these QLC drives, which come in 15 or 30 terabyte size. And if you multiply that by 44, then you see that on a single, small, very compact 2 rack unit system, you can already store half a petabyte or full petabyte of data in this very small but powerful box. And we pair that together with 12 of these storage class memory drives, which, as we discussed, we use as the write buffer. Otherwise, this Nvme enclosure itself does not run any of the storage logic. We completely separated that by connecting all of the Nvme enclosures that we have in the system to what I call in this picture here the protocol servers. This is where the actual file system logic runs. Again, that's a 2 rack units box, out of which you see 4 small boxes coming. That's because it's a quad server enclosure. So the single box already contains 4 independent servers. A very special aspect of the VAST architecture is that we connected via this special backend fabric here, network fabric. We connected all of the protocol servers in the system to all of the drives that we have in the Nvme enclosures in the system. That's a new model that did not exist like this before, so we thought we should give it a new name. We call it the DASE architecture. Disaggregated, shared everything. Disaggregated because we disaggregated the drives from the actual protocol servers, or the file system, runs and share everything, because all of these protocol servers actually have access to all of the drives. They all share all of the drives. And that enabled us to get to very high performance without the need for one of these classic, more complicated parallel file systems, and instead only through the standard protocols like NFS that everyone knows and loves for their simplicity and ease of use. So thanks to the fact that we have this special DASE architecture where all the protocol servers have access to all the drives and all the data in the backend, from the client point of view, from your HPC compute node point of view, now it does not matter anymore which of the I/O requests goes to which of the servers that we have in the system, because any of the servers is connected to all of the data, and so we directly give the reply, right? So that's a big advantage. But the problem with NFS traditionally is that when you have an NFS mount point, you can only specify a single server IP address. So that means even in a system like that, where you can have an arbitrary number of servers, the single client can always only talk to a single server of the classic approaches. That limits the performance that the single compute node can get. That, of course, in turn limits what you can do with your storage system or your nice GPU server. So we wanted to overcome this limit, and thanks to this special VAST Data architecture, we were able. On to the next slide. Yes. Thanks to the special VAST Data architecture, we were able to introduce a new concept to NFS-based storage that we call NFS multipathing. With NFS multipathing, now the single client really has the ability to have specified, instead of only a single server IP address, a range of server IP addresses, so that it can really establish connections to all of the servers that we have in the system and talk to all of them in parallel, which of course gives you much, much better performance for your applications, right? Many more cat images per second, let's say in a simple example. But we did not want to leave it with that. We designed VAST Data to be what I call a multi-protocol system. So NFS is typically through multipathing, the protocol that you can use to access it from your HPC cluster from multiple compute nodes in parallel. But then sometimes your workstations that you might have under your desktop, they might be running Windows, and you want to run graphical applications there to look at your data afterwards. So Windows access is also important. That's why we support the SMB protocol for Windows access as well to the same data, right? So it's no problem to access the same data from your HPC compute nodes during your simulations, and also from your Windows workstation or laptop at the same time. But even better, VAST Data also supports S3 as a so-called object or cloud-native storage protocol. It's a protocol that's optimized especially for wide area transfers of data, so especially interesting if you want to share access to the system with other universities, right? Make it very easy to transfer the results somewhere, or make the results available to other researchers, or maybe even in the future do things like cloud bursting, where you only have a moderate sized HPC system here, but for certain bursts of applications, you would use public clouds and need to have your data, of course, accessible there, otherwise you have nothing to compute on in the cloud. So that's a special aspect of VAST Data systems, that it's this multi-protocol namespace where you really have super flexible access to your data from everywhere in the world. Okay, and I thought it might be nice to look at this multi-pathing live and in action. So let's see if the live demo works out. Always fun with a live demo, you never know if it will work out or not. So far, are there any questions in the meantime that I should answer? Good.
Yes, sir.
Yeah, okay.
About fast NFS. Okay? About fast NFS.
Yes, fast NFS, yeah.
Is it like HDFS?
It's better than HDFS because it allows full random access to all of the files that you have.
Okay.
So HDFS, yeah. Yeah, so you can consider it a full drop-in replacement or an alternative, a more flexible alternative to HDFS. Right? HDFS was basically designed several years ago under the assumption that the networks are always very slow, right? So you cannot have a centralized storage system, and rather need to have the data on your compute nodes, right? Internal in the compute nodes. That's the basic. Yeah. So that's no longer true these days. Right? These days the networks have become very fast, and the problem with having the data on the compute nodes is that the compute nodes are typically very unreliable. So you have to store typically 3 copies of your data to make sure that you don't lose it. And that makes the systems at larger scale very, very expensive because you have to buy 3 times the capacity. Yeah.
What is the same? They are the same.
Yeah, you can use it for the same use cases where you previously used HDFS and for more. Right? These days, all the big data area tools that used HDFS originally, they have been ported to use S3 nowadays as an alternative protocol. Yeah, glad I could help. Okay, so far it's looking good with the live demo. So what do I have here? Here I'm on one of our servers in the lab. It's the DGX A100 system. The DGX A100 is what I would call a very powerful beast. It contains 8 A100 GPUs from Nvidia in a single server. And together with these 8 GPUs, it also contains 2 very fast 200 gigabit network cards, just emphasizing how much data this machine can theoretically consume. Here we have connected it only to the small entry-level VAST system, the minimum system, which has one of these protocol server enclosures containing the 4 servers, and only a single one of these Nvme enclosures. So the smallest VAST system that you can build, connected to only a single server, and using only a single NFS mount point. And as a matter of fact, as it should be for a live demo, one of the GPUs failed, so we only have 7 GPUs available for the server, but it doesn't really matter. I'll just start a quick benchmark here. The benchmark tool that I'm using is called Bencho. It's a tool that I wrote myself, but that doesn't really matter. I wrote it because originally Nvidia came out with a new concept to get data into the GPUs, which is called GPU Direct Storage. It's a way for a storage system to get the data from the network card directly into the GPU memory. Previously, believe it or not, this was not possible. You always had to read the data into the main memory of the computer first, and then afterwards you had to copy it over from there into the GPU memory to do something with the data afterwards. So what we are doing here with Bencho, the simple benchmarking tool, is we are reading data, -R. We're using 256 threads because the DGX A100 is a very powerful beast and has 256 logical CPU cores. We are reading a bunch of large files that could, for instance, contain lots of our cat images from the Hello Cairo folder, as I called it. And we are transferring this data into the 7 GPUs that are currently functional on the system. And let's just see what happens when I start. Right? So we're just reading data into the GPUs. We're not doing any computation actually on the GPUs, just transferring the data. thing is that we are getting some nice throughput from our very small 2 rack units Nvme Enclosure. You can see here in this column at the very top, the aggregate throughput is somewhere around 27 gigabytes per second. That's sure impressive. But the thing that I actually wanted to show you is here in the NVIDIA SMI tool. The NVIDIA SMI tool can show the live utilization of the pipelines of the GPUs. I made the font a bit larger so that you can see something here, so you cannot see all the GPUs that are currently in the system, only 4 of them, and one of them is currently non-functional, unfortunately, but that doesn't really matter. The problem that I wanted to show you is here. We're just transferring the data into the GPUs at 30 gigabytes per second, not doing any calculation on the data, just transferring. And you can see that the NVIDIA SMI tool is showing us that the GPUs are already utilized between 30 to 40%. That means without doing any calculation on the data already, you lost 30 to 40% of the computational power of the GPUs already, right? Just for the data transfer without any calculation. That's a problem, of course, and that's why it was so important for us to work together with NVIDIA, who's actually one of the investors in VAST Data company, to support this new approach, which is called GPU direct storage. So now, this was the classic approach where we had to read the data first into the main memory and afterwards copy it over to the GPUs. Now we are doing the same thing, but we do that we can do exactly this approach. So the only thing I changed is that I added the --GPS parameter here to make it use GPU direct storage and transfer the data directly from the network cards in the GPU server into the GPUs where it actually belongs. Okay, on the one hand, we're ending up with about the same performance as before. That's not the interesting part. The interesting part is when we now look at the GPU utilization. Again, we're transferring data into the GPUs at the same speed as we did before, and it's the same data. But here, you see 0% GPU utilization now for the transfer. That's the magic of the GPU direct storage approach, that the GPUs themselves are not involved at all in the data transfer. The network card makes all this happen by putting the data directly into the memory of the GPUs without the GPUs needing to do anything for it. And that means you have now 30 to 40% more cycles available on the GPUs to run your actual applications. That's why GPU direct storage is so important. Good. And we could also look maybe quickly at the VAST user interface in case that's interesting. Okay, I hope this is not too small to see. I told you we also try to make everything super easy to manage. So in a VAST storage system, you should not have to waste any dedicated resources or storage system administrators that have to take care of the storage every day. So we built a modern, very easy and intuitive web front end to manage the storage system that can always show you the green lights when everything is functional, up and running. That can also show you the red lights over here, like just before lifetime, not everything is working. So we actually have 2 failed drives in the system at the moment, but it doesn't matter, the performance is still great. And now, if we wanted to, we could actually drill down a bit further and see under the hood what's happening while we're reading the data. And yeah, here we see the 4 servers that are in the system, and as it should be, the single client, that's the magic of this NFS multipathing approach, the single client is really spreading the workload across the 4 servers that we have in the system. That's the only way how this client can actually get to this high performance, by talking to all of the servers in parallel. And the other thing for larger storage systems is, of course, to always have a good overview of where the capacity of the storage system has been used. For that, we added what we call the capacity view, based on this nice pie chart. Here in the center, you can see the root, so the top level directory of your VAST storage system, and then if you go into the outer rings, it's the first subdirectory level of the storage system, and then the next outer ring is the second subdirectory level. So this pie chart here makes it very easy to see that this directory, it will be a project, a research project, for instance, in your case, is using up a quarter exactly of the space that we have on the storage system, right? So that makes it easier to predict when you will be running out of space or which projects consume the most space, so that you can consider extending the system later. Okay, and I told you it's a multi-protocol system, so you probably have an idea already. But if I wanted to, I could now read from the same host the same data again via S3 instead of the Hadoop file system, for instance. It's another thing that eventual benchmarking tool supports. So in this case, I'm giving it a range of VAST server IP addresses as S3 endpoints, and otherwise it's reading the same files from my Hello Cairo folder, again on the single client, now through a completely different protocol, through S3 as a cloud native protocol that I could also be using from a completely different location or from the cloud. And again, I see that I'm ending up at around 30 gigabytes per second. That's also something very untypical for storage systems, that they have such good performance for S3 as an access protocol. Okay. Unless there are any further questions at this point, we'll continue with the slides. You're good? Perfect. That makes me happy. Okay. At some point, of course, no matter what storage system size you start with, the storage system will be full, so you will say, I need to add more capacity or more performance, because now my GPU use case is really taking off. I have a great new idea that's becoming more and more important, so I need to extend the storage system. That's of course always possible with the VAST system. You can always add more protocol servers that you saw in the middle layer to have more performance. And you can at any point in time also add more Nvme enclosures to have more capacity in the system. In fact, VAST is actually very successful also with the larger customers, which hopefully shows that we must have done something right and important, because our customers build so large systems with us. This is a 25 petabyte system, and one of our industry customers from the finance industry, they loved the system so much that they immediately ordered another 25 petabyte system like this. And just to emphasize again that performance with the VAST storage system, especially for NFS and S3, is not comparable to the performance of any other storage system you might have seen before. We could take this DGX A100 use case even further and fully saturate the 8 200 gigabit GPUs that are in these servers and transfer 160 gigabytes per second into the single GPU server if it should really ever be required. Okay, otherwise, with respect to features, I guess you're probably more interested in running applications on the storage system, so the features themselves are not so super interesting to do, but the VAST storage systems come with all the nice bells and whistles I would say that you could imagine for a storage system. For instance, we have the capability to do instant snapshots. That means if you accidentally delete your files, which happens to some people apparently, it's not a problem at all. You can just easily restore these files themselves from the snapshots. We can also do encryption at rest. Some of our customers ask us for encryption because they store sensitive medical data on these systems. So let's say, for instance, if a drive on these systems fails and needs to go into the trash, and nobody should be able to do anything with the data on these drives. That's why the encryption at rest is so important, and we support that as well. Yeah, we can do replication to other sites, right? So if here in Cairo we would have a VAST storage system, and in some other place there would be another VAST storage system, then these could replicate their research data between each other to make the sharing easier and things like that. But the one that we do. So let's talk a bit about that. Similarity is now this special approach to data compression, which I would say is almost magic from the mathematical perspective. I'll not go into all the mathematical details, but maybe here are some people who are smart enough to figure it out themselves. I haven't fully figured it out myself yet, I have to admit. For me it's still magic in the most part. But what we are doing here is global compression. So many storage systems these days already support what is called compression. What they don't tell you is that this refers to only local data compression. So let's say you ingest a new megabyte of data into a storage system, a new cat image, let's say, right? And the storage system only looks at this new small piece of the data and tries to reduce it within itself into something that's hopefully a bit smaller than originally. But the storage system, we call it local because the storage system has no ability to look left and right whether there are already similar images or blocks in the system, which we could use to reduce the data further. That's why we call it local compression. Another well-known approach in the storage industry is called deduplication. Deduplication means when you insert something into the storage system, like a new cat image, the storage system tries to find out whether an exact copy of this already exists somewhere in the storage system, and then knows that it does not need to store this file or this block twice, and can just internally keep track of that this file should exist again in a different location where you stored the copy. The problem with this is that it can only find exact copies of the data, right? And it's rare that you store the same cat image twice. It's much more probable that you will have similar images but not completely identical images. And that's why we spend so much research on trying to find a combination between these two. Right? Deduplication is global but only finds exact copies. Compression can find similar things but only locally within very small areas of the storage system. So that's the game-changing idea that we came up with and that we call VAST Data Similarity Reduction. VAST Data Similarity Reduction can really find out for everything new that you store inside your storage system, not only whether there are identical copies of this, but whether there are similar things to this at the global level, right? That means we had to come up with a new hashing algorithm that has a special property of when two hash values of the data are very close to each other, right? Then there's a high probability that these two blocks are rather similar, so we only need to store the differences between the two blocks, and so we can save a lot of capacity on the storage systems. And our storage systems support what we call call home functionality. That means the storage systems in regular intervals support report their health status and things like the data reduction factor to our central database. And from that, we know, for instance, that across all our HPC customers, we get a 3-to-1 data reduction factor. That means if they want to store 3 petabytes of data on their systems, they only need to buy 1 petabyte of hardware for that. That's the magic of the data reduction. Good. Let's get over that one. the nice user interface you already saw. Hopefully gives you always full control and makes it very easy for you to adopt a VAST storage system because there's nothing to manage. It just always is online and always works, and otherwise through the call home functionality our support takes care of whatever problems might come up with the system. So that's the reason why we call the company VAST Data, right? Because nowadays there are these vast amounts of data that we need to train our AIs on, and that's also why we call the product universal storage, because we believe that it's really appropriate for anything that you might want to do with your data in modern research. The Lawrence Livermore Mission Lab, maybe you have heard of this, is actually one of the top world-leading HPC organizations in the United States. They gave us a quote saying that their VAST system, which gives them the fast and seamless access to all of their tiny files, is one of the key factors to their success. So they really make it available to 22 different clusters, HPC systems that they have in their facilities. They use it as the classic HPC scratch space and also for their AI training to solve all these tough challenges. And I thought better than me telling you about this, maybe I could play a quick 2-minute video where they themselves are sharing their thoughts about that. And again, this is experimental. Let's try if this works out. Me holding the microphone close to the laptop. Which is skip over that, thanks for waiting. But that's the fun of live presentations, right? Okay, so let's look at other customers. For instance, the Martino Center doing biomedical imaging, like cancer research that we talked about, right? So some of the really important things that move our society forward. They are very happy with the VAST system and the support they get together with their VAST systems. Because one of my main interests when I am in the field like today is of course not only to provide a storage system that allows you to do much better research today. My job is to also learn everything I can about the research that you're doing so that I can be sure that we also build the best storage system for you tomorrow and the day after and next year and so on. Next one, in retail, another well-known medical company. Right? We're still wearing the masks mostly today, so we haven't forgotten COVID yet, unfortunately. But we are very proud that we could help in retail. They told us that COVID research test runs for analysis came down thanks to the VAST storage system from 24 hours of runtime, so very non-interactive and long waiting time, to now only 15 minutes. That's the difference that the storage system can make for the HPC and AI workloads that you're doing, right? Agoda, getting back to HDFS, for instance, they used to have this classic Hadoop-based architecture, which was based on the foundation that the networks are rather slow, which was true back in the days, and that you had to store the data inside the compute nodes instead of having a centralized storage system, but that's all no longer true today. Having the data in the compute nodes and having to have 3 copies of the data just makes the storage systems way too expensive and not scalable. So Agoda converted their systems to VAST and is of course now running much better analytics, which helps all of us, by the way, of course, if we're going on vacation, right? Because Agoda's job is to make the perfect recommendations for what you can do during your vacation. For that, they need to understand which interests you have, and programming that for a human these days has become so complicated that you actually need AI again to really have a good understanding and with the perfect recommendations for you to have the perfect vacation afterwards. Okay, this is the last one, and actually the one that I like most because it best reflects what all this is about. This is dug down under geophysics, headquartered in Down Under in Australia, but with HPC cloud service centers all around the globe. So they are HPC service provider. They give other people access to their HPC systems and help them run their applications and also provide the knowledge to build the right applications. And what they are changing is that VAST hasn't just changed the way they store data, it has changed the relationship they have to the data. Right? That emphasizes that it's not about just having a bit faster access to the data, but actually being able to do new things with the data once the access to the data becomes so much faster and more seamless from other parts of the world and things like that. So with the VAST storage system, right, finally we have the same in HPC that a supercomputer is a machine to turn a compute-bound problem into an I/O-bound problem, into a storage-bound problem. That's an old saying in the HPC world, right? So with VAST, we try to make it the other way around again. Solve the storage problem and turn it back into a compute problem so that you can work on figuring out the actually important part, how to compute the important things today and not worry about the storage system anymore. And that's it from me. Thank you very much for listening. If there are any questions, then I'm happy to answer. Yeah?
Thank you very much for this nice and interesting talk.
Thank you.
My question is about we are actually interested in use our HPC data sources outside EOS. Actually, we are participating in worldwide experiments as Sven, science rockets, science, and also the seasoning, the super qualification, which is so we give our scientists the opportunity to use the facilities outside using our online.
Yeah.
I think there needs some protocols for communication. Can you give us some lights about these tasks?
Yeah. Wow. I'm impressed. I wasn't aware that you are already so well connected with other facilities in different areas, and this would already be important to you. That's great to hear, of course, because this is where the S3 protocol becomes so relevant. Right? NFS is a protocol that's great to access the data locally from your GPU service, for instance, with the maximum speed, but to share it in a geographically distributed way, you need a protocol like S3 that is made for this wide area transfers that does not assume low latency access to the data. That's why it's so important that the VAST storage system support S3, because that makes it very easy to access the data also from other facilities in other parts of the world. And we have completely integrated this in the way that every user who will have access to a certain file via NFS automatically also has access to the file via S3 as the wide area protocol. So it's nothing special that we have to do for it, it just works with the VAST system. Another very important one, right? Yeah, sometimes, or especially also during COVID, you want to access your data from home, right? Your workstation is not always close to the HPC cluster. So what can we do for that? The answer is actually, again, S3 is the wide area transfer protocol. Even though it's not as wide as to a completely different location to get to your home, but it's still from perspective wide area transfer. So the way this works is you would just make the VAST system directly available on the internet, and then, but it's fully protected in the sense that only the people who should have access to the data can access
This
it.
is my concern actually. What about the cybersecurity? There is any impact on the account, the HPC account for anyone? How we can secure the data on our device?
Yeah. If you don't want to make the system itself directly available on the internet, the typical approach I would say is to have a VPN solution, a virtual private network solution that is very high security and ensures that. Right, yeah. So it's that is not integrated into the VAST system, right? It's a special mechanism to bring your laptops at home into the virtually same network that we have at the university, right? For that, there are very strong security mechanisms in place, and so that way you avoid having your VAST system directly on the internet because it's only on this VPN where only people with a special permission can access the system. Yeah, it's actually the same approach that we're using here. I'm now connected to one of these VPNs in the VAST lab, otherwise I could not access all the systems from the internet. Thank you for the excellent question. Yeah. Oh yeah, another question. Yes? Oh, thank you. I think I need to come a bit closer because it's hard to stand here.
How do you achieve the discovery codes with encryption of the data? And the second thing that you have mentioned, the IT agility. Concept of the IT agility. Can you explain more about this one, please? Thank you.
So IT agility, basically the agility limited if you build storage systems only for a particular purpose, right? Then they are either only slow and weak, which means you can only use them for slow accesses where you have a lot of capacity, or they are small and fast, right? Then again, are very limited in their usefulness. So that's what that's our approach to try to make it future-proof in the things that we build. And storage system, right, which has typically so much more. Here I'm showing that you can reach 30 or more gigabytes from a single DGX server. To be honest, in practice, I haven't seen anyone consuming so much data actually from a single GPU server. It's still important because of what I showed you, that you're using GPU cycles without the GPU direct storage approach, even if you're transferring data at lower speed. But in general, our assumption is the VAST systems are so fast that you cannot only use them for HPC, you can put everything that you have on them, like the user own directories, which used to be separate virtual machines or whatever I might be running. The other thing for IT agility is, of course, that I'm here in the field trying to learn from you what you need today, what you might not have, or what you might need tomorrow to do more great research, so that we can make sure that these things are integrated into a VAST system whenever you need that. Maybe another one is that our customers love to build big VAST systems, so put a lot of data on them, and that means if at some point in the future you would like to expand them, but the old hardware is no longer available, then it would be very painful to have to migrate all of the data to a completely new storage system. That would not be very agile, right? It would be rather disruptive for the whole research that you're doing. So for that, we're making a guarantee that we call the infinite storage lifecycle. Basically, it just means we guarantee that it will always be able to combine old and new hardware generations of VAST together in the same system. So with VAST, you never ever have to migrate to a completely new system, where you can always combine old and new hardware into the same system. And so if you decide at some point that the old hardware is no longer good enough, then you can just configure it out of the system, but you have a completely separate system. Does that answer the second question? Good. And the first one was about encryption, you said?
How do you put the data and then is the data allowed to be stored?
Okay. Yeah, it's the encryption that we are doing is called encryption at rest. It means the data encrypted on the drive in a way that if you would pull out one of the drives of the system and try to get data from it, that wouldn't work because it it's globally this encryption that we use. It's not encrypted different ways for different users. It's just encrypted in a way that if someone gets access to this drive, if it's pulled out of the system, you cannot read the data. That's typically the most important thing to protect sensitive medical data. Yeah, the other thing that we're working on is what we call on-the-wire encryption. So if the data is being transferred from the compute node to the storage system, then it's also encrypted in case someone, the man in the middle, so-called, could get access to this data stream, that they can't use the data anymore. But that typically costs a bit of performance, so I would not recommend to enable it for an HPC cluster purposes. It's maybe more relevant if you're doing indeed transfers over the internet from your home laptop, right? Then it's a more dangerous environment there. This type of wireless encryption becomes important, and that's what we also support. Thank you.
Last one is about the data loss. You said that it's not what we call exactly, as we call it exactly. So the risk of data loss, what is the probability for it? That's just my thing.
Yeah, data loss. That's actually a very good one about which I haven't talked, even though it's one of my favorite topics. So maybe I will quickly go back to the slides. Do I have more time? Yeah, I guess I have more time, right? Yeah. Okay. So, what do you do to make sure that you never ever lose your data? So here we have the VAST architecture. Again, as you might remember, first line are the compute nodes, not relevant for your data protection. Relevant for your data protection are the middle layer here, our protocol servers, so the actual file system and object storage logic runs, and the Nvme Enclosures. To make sure that the Nvme Enclosures are always available, we do what you can't see here in the picture. We have two servers inside these Nvme Enclosures. and the drives are physically shared between these two servers. So if one of the servers in the enclosure fails, the other one just takes over all of the drives and still provides access to all of the data. At the protocol server layer, it's also very nice in the sense that from the client point of view, the protocol servers all look the same, right? The client doesn't even care about which server it's talking to. It doesn't notice any difference between the servers. That means in a system like this, where we would have a total of 16 servers, 16 of these small boxes coming out, 15 of them can fail, and the remaining single one would still provide access to all the data, because it's really connected to our backend network, to all of the drives that we have in the system, so it can still provide access to all of the data. You could say in a system with 100 servers, 99 of them could fail, and the remaining single one would still provide access to all of the data. So very high level of resilience. And we make that possible by automatically moving the IP addresses from the failed servers just over to the remaining servers. The clients just reconnect and everything continues. What I abstractly call here the backend network fabric is actually also a redundant pair of Mellanox switches. Again, one of them can fail, everything is redundantly connected, the system just continues. Which brings us to the last and maybe most interesting part. What do we do if one of the flash drives here fails, of the QLC flash drives? For that we do what we call +4 erasure coding. So assuming we have a single box with these 44 QLC drives, we do 36 +4 erasure coding. That means you can use arbitrary 4 drives in this box at the same time without losing access to your data. That's a much higher protection level than classically known through approaches like layer 6, where you typically have an array of 8 + 2 drives. That means you use 2 out of 10 drives, so 20% for the erasure coding overhead, right? But we wanted to reduce that overhead, so we do what we call 36 +4 in this enclosure, meaning we use only 4 out of 40 drives, so only 10% of the capacity, but still have much higher protection level because you can now use arbitrary 4 drives instead of arbitrary 2 drives only. That gets us into the very comfortable situation that if you ever only use a single drive in the system, we don't even consider it a critical situation because you could use 3 more drives before it becomes critical. And that means when only a single drive fails, we intentionally throttle the rebuild of this data to about megabytes per second, so the rebuild can take a day or maybe even 2, and overnight after a drive failed. That's why we intentionally throttle the rebuild speed to make sure that we still have high performance even after a failure. Thank you for asking this. Oh yeah, one more, yeah? I'll come over to you. Yourself would get 3 to 1 data reduction of your data. Yeah, okay. Oh yeah, that's because we're using what we call lossless. It's the same as when on Windows web or so-called tar archive. You know the things? No? Pagoda is doing everything in real time because you're in real time on their website, but they need to make real time AIs to make the perfect recommendations. Yeah. Do you know zip files on Windows where you can compress multiple things together? Yeah, like Breuner, right? Okay. Yeah. So basically, how this compression works is it tries to find identical sequences of bits, and then builds a so-called dictionary, right, where it stores, where it stores all these bit sequences in a special area of the file, and then just references, okay, to this part of the file belongs this word from the dictionary, right, this sequence of bits. That's how you avoid storing the same bit sequence again and again, but still preserve the original bit sequence because you keep track of which bit. Mathematically it's super interesting, and there are many different compression algorithms that can do this, which have pros and cons. Some are more computationally intensive and thus are slower, right? Some, but then lead to better data reduction afterwards, and some are faster and thus lead to worse data reduction. So it's always a trade-off, and also an area of research to come up with new algorithms for lossless compression. Okay. Any more questions? Looks like we're good for the moment, and I'll be around, of course, so happy to answer questions at any time later. Thank you so much.